In quantum mechanics, Ket notation is a standard notation for describing quantum states, composed of angle brackets and vertical bars. It can also be used to denote abstract vectors and linear functionals in mathematics. In such terms, the scalar product, or action of a linear functional on a vector in a complex vector space, is denoted by consisting of a left part, called the br, and a right part, called the ket, kt. The notation was introduced in 1939 by Paul Dirac and is also known as Dirac notation. Though the notation has precursors in Grassmann's use of the notation for his inner products nearly 100 years earlier, Ket notation is widespread in quantum mechanics. Almost every phenomenon that is explained using quantum mechanics, including a large portion of modern physics, is usually explained with the help of Ket notation. Part of the appeal of the notation is the abstract representation independence it encodes, together with its versatility in producing a specific representation without much ado, or excessive reliance on the nature of the linear spaces involved. The overlap expression is typically interpreted as the probability amplitude for the state psi to collapse into the state phi. Vector spaces. Background. Vector spaces in physics. Basis vectors allow any Euclidean vector to be represented geometrically using angles and lengths in different directions, i.e., in terms of the spatial orientations. It is simpler to see the notational equivalences between ordinary notation and Ket notation. So, for now, consider a vector A starting at the origin and ending at an element of 3D Euclidean space. The vector then is specified by this endpoint, a triplet of elements in the field of real numbers, symbolically dubbed as A3. The vector A can be written using any set of basis vectors and corresponding coordinate system. Informally, basis vectors are like building blocks of a vector. They are added together to compose a vector, and the coordinates are the numerical coefficients of basis vectors in each direction. Two useful representations of a vector are simply a linear combination of basis vectors and column matrices. Using the familiar Cartesian basis, a vector A may be written as respectively, where x, a, e, z denote the Cartesian basis vectors and x, I, Arizona are the corresponding coordinates, in the x, y, z directions. In a more general notation, for any basis in 3D space one writes generalizing further. Consider a vector A in an n-dimensional vector space over the field of complex numbers, symbolically stated as an. The vector A is still conventionally represented by a linear combination of basis vectors or a column matrix, though the coordinates are now all complex-valued. Even more generally, A can be a vector in a complex Hilbert space. Some Hilbert spaces, like N, have finite dimension, while others have infinite dimension. In an infinite-dimensional space, the column vector representation of A would be a list of infinitely many complex numbers. Ket notation for vectors rather than bold type, over arrows, underscores etc. Conventionally used elsewhere. Dirac's notation for a vector uses vertical bars and angular brackets. When this notation is used, these vectors are called ket readers, ket A. This applies to all vectors, the resultant vector and the basis. The previous vectors are now written or in a more easily generalized notation. The last one may be written in short as note how any symbols, letters, numbers, or even words, whatever serves as a convenient label, can be used as the label inside a ket. In other words, the symbol has a specific and universal mathematical meaning, while just the by itself does not. Nevertheless, for convenience, there is usually some logical scheme behind the labels inside kets, such as the common practice of labeling energy eigenkets in quantum mechanics through a listing of their quantum numbers. Further note that a ket and its representation by a coordinate vector are not the same mathematical object. A ket does not require specification of a basis, whereas the coordinate vector needs a basis in order to be well defined. In this context, one should best use a symbol different than the equal sign. For example, the symbol readers is represented by inner products and bars. An inner product is a generalization of the dot product. The inner product of two vectors is a scalar. Ket notation uses a specific notation for inner products. For example, in three-dimensional complex Euclidean space, where denotes the complex conjugate of I. A special case is the inner product of a vector with itself, which is the square of its norm. Ket notation splits this inner product into two pieces, the bra and the ket. Where is called a bra, readers bra A, and as a ket is above. The purpose of splitting the inner product into a bra and a ket is that both the bra and the ket are meaningful on their own, and can be used in other contexts besides within an inner product. There are two main ways to think about the meanings of separate bras and kets. Bras and kets as row and column vectors for a finite-dimensional vector space, using a fixed orthonormal basis. The inner product can be written as a matrix multiplication of a row vector with a column vector. Based on this, the bras and kets can be defined as, and then it is understood that a bra next to a ket implies matrix multiplication. The conjugate transpose of a bra is the corresponding ket and vice versa, because if one starts with the bra then performs a complex conjugation, and then a matrix transpose, one ends up with the ket bras as linear operators on kets. A more abstract definition, which is equivalent but more easily generalized to infinite-dimensional spaces, is to say that bras are linear functionals on kets, i.e., operators that input a ket and output a complex number. The bra operators are defined to be consistent with the inner product. In mathematics terminology, the vector space of bras is the dual space to the vector space of kets, and corresponding bras and kets are related by the Riesz representation theorem. Non-normalizable states and non-Hilbert spaces. Ket notation can be used even if the vector space is not a Hilbert space. In quantum mechanics, it is common practice to write down kets which have infinite norm, i.e., non-normalizable wave functions. Examples include states whose wave functions are Dirac delta functions or infinite plane waves. These do not, technically, belong to the Hilbert space itself. However, the definition of Hilbert space can be broadened to accommodate these states. The Ket notation continues to work in an analogous way in this broader context. For a rigorous treatment of the Dirac inner products of non-normalizable states, see the definition given by D. Carphy. For a rigorous definition of basis with a continuous set of indices and consequently for a rigorous definition of position and momentum basis, see. For a rigorous statement of the expansion of an S-diagonalizable operator, or observable, in its eigenbasis or in another basis, see. Banach spaces are a different generalization of Hilbert spaces. In a Banach space B, the vectors may be notated by kets and the continuous linear functionals by bras. Over any vector space without topology, we may also notate the vectors by kets and the linear functionals by bras. In these more general contexts, the bracket does not have the meaning of an inner product, because the Riesz representation theorem does not apply. Usage in quantum mechanics. The mathematical structure of quantum mechanics is based in large part on linear algebra. Wave functions and other quantum states can be represented as vectors in a complex Hilbert space. In Ket notation, for example, an electron might be in the state psi. Quantum superpositions can be described as vector sums of the constituent states. For example, an electron in the state 1 plus I2 is in a quantum superposition of the states 1 and 2. Measurements are associated with linear operators on the Hilbert space of quantum states. Dynamics are also described by linear operators on the Hilbert space. For example, in the Schrödinger picture, there is a linear time evolution operator U with the property that if an electron is in state psi right now, then in 1 second it will be in the state U psi, the same U for every possible psi. Wave function normalization is scaling a wave function so that its norm is 1. Since virtually every calculation in quantum mechanics involves vectors and linear operators, it can involve, and often does involve, Ket notation. A few examples follow. Spinless position space wave function. The Hilbert space of a spin zero-point particle is spanned by a position basis, R, where the label R extends over the set of all points in position space. Since there are an uncountably infinite number of vector components in the basis, this is an uncountably infinite-dimensional Hilbert space. The dimensions of the Hilbert space and position space are not to be conflated. Starting from any ket psi in this Hilbert space, we can define a complex scalar function of R, known as a wave function. On the left side, psi is a function mapping any point in space to a complex number. On the right side, psi equals d3 r psi, R is a ket. It is then customary to define linear operators acting on wave functions in terms of linear operators acting on kets by, for instance, the differential operator must be understood to be an abstract operator acting on kets that has the effect of differentiating wave functions once the expression is projected into the position basis, even though, in the momentum basis, the operator amounts to a mere multiplication operator. Overlap of states. In quantum mechanics, the expression is typically interpreted as the probability amplitude for the state psi to collapse into the state phi. Mathematically, this means the coefficient for the projection of psi onto phi. It is also described as the projection of state psi onto state phi. Changing basis for a spin 1/2 particle. A stationary spin 1/2 particle has a two-dimensional Hilbert space. One orthonormal basis is, whereas the state with a definite value of the spin operator sz equal to +1/2 and is the state with a definite value of the spin operator sz equal to -1/2. Since these are a basis, any quantum state of the particle can be expressed as a linear combination of these two states, where a psi, b psi are complex numbers. A different basis for the same Hilbert space is defined in terms of Sx rather than Sz. Again, any state of the particle can be expressed as a linear combination of these two. In vector form, you might write depending on which basis you are using. In other words, the coordinates of a vector depend on the basis used. There is a mathematical relationship between a psi, b psi, c psi, d psi, c change of basis. Misleading uses. There are a few conventions and abuses of notation that are generally accepted by the physics community, but which might confuse the non-initiated. It is common among physicists to use the same symbol for labels and constants in the same equation. It supposedly becomes easier to identify that the constant is related to the labeled object, and is claimed that the divergent nature of each will eliminate any ambiguity and no further differentiation is required. For example, alpha equals alpha, where the symbol alpha is used simultaneously as the name of the operator alpha, its eigenvector, alpha, and the associated eigenvalue alpha. Something similar occurs in component notation of vectors. While psi is traditionally associated with wave functions, psi may be used to denote a label, a wave function or complex constant in the same context, usually differentiated only by a subscript. The main abuses are including operations inside the vector labels. This is usually done for a fast notation of scaling vectors. E.g., if the vector alpha is scaled by √2, it might be denoted by alpha √2, which makes no sense since alpha is a label, not a function or a number, so you can't perform operations on it. This is especially common when denoting vectors as tensor products, where part of the labels are moved outside the designed slot, e.g., alpha equals alpha square root 2 1, alpha square root 2 2. Here part of the labeling that should state that all three vectors are different was moved outside the kets, as subscripts 1 and 2. And a further abuse occurs, since alpha is meant to refer to the norm of the first vector, which is a label denoting a value. Linear operators. Linear operators acting on kets. A linear operator is a map that inputs a ket and outputs a ket. In other words, if A is a linear operator and psi is a ket, then A, psi is another ket. In an n-dimensional Hilbert space, psi can be written as an n times 1 column vector, and then A is an n times n matrix with complex entries. The ket A, psi can be computed by normal matrix multiplication. Linear operators are ubiquitous in the theory of quantum mechanics. For example, observable physical quantities are represented by self-adjoint operators, such as energy or momentum, whereas transformative processes are represented by unitary linear operators such as rotation or the progression of time. Linear operators acting on bars. Operators can also be viewed as acting on bars from the right-hand side. Specifically, if A is a linear operator and phi is a bra, then phi A is another bra defined by the rule. This expression is commonly written as, in an n-dimensional Hilbert space, phi can be written as a 1 times n row vector, and A is an n times n matrix. Then the bra phi A can be computed by normal matrix multiplication. If the same state vector appears on both bra and ket side, then this expression gives the expectation value, or mean or average value, of the observable represented by operator A for the physical system in the state psi. Outer products. A convenient way to define linear operators on Hilbert space H is given by the outer product. If phi is a bra and psi is a ket, the outer product denotes the rank 1 operator with the rule. For a finite-dimensional vector space, the outer product can be understood as simple matrix multiplication. The outer product is an n times n matrix, as expected for a linear operator. One of the uses of the outer product is to construct projection operators. Given a ket, psi of norm 1, the orthogonal projection onto the subspace spanned by psi is Hermitian conjugate operated just as kets and bras can be transformed into each other. The element from the dual space corresponding to A, psi is psi, where A denotes the Hermitian conjugate of the operator A. In other words, if and only if A is expressed as an n times n matrix, then A is its conjugate transpose. Self-adjoint operators, where A equals A, play an important role in quantum mechanics. For example, an observable is always described by a self-adjoint operator. If A is a self-adjoint operator, then psi is always a real number. This implies that expectation values of observables are real. Properties. Ket notation was designed to facilitate the formal manipulation of linear algebraic expressions. Some of the properties that allow this manipulation are listed herein. In what follows, C1 and C2 denote arbitrary complex numbers, C denotes the complex conjugate of C, A and B denote arbitrary linear operators. And these properties are to hold for any choice of bras and kets. Linearity. Since bras are linear functionals, by the definition of addition and scalar multiplication of linear functionals in a dual space, associativity given any expression involving complex numbers, bras, kets, inner products, outer products, and/or linear operators. Written in Ket notation, the parenthetical groupings do not matter, for example, and so forth. The expressions on the right are allowed to be written unambiguously because of the equalities on the left. Note that the associative property does not hold for expressions that include nonlinear operators, such as the antilinear time reversal operator in physics. Hermitian conjugation. Ket notation makes it particularly easy to compute the Hermitian conjugate of expressions. The formal rules are: The Hermitian conjugate of a bra is the corresponding ket, and vice versa. The Hermitian conjugate of a complex number is its complex conjugate. The Hermitian conjugate of anything is itself, i.e., equals x. Given any combination of complex numbers, bras, kets, inner products, outer products, and or linear operators, written in Ket notation, its Hermitian conjugate can be computed by reversing the order of the components, and taking the Hermitian conjugate of each. These rules are sufficient to formally write the Hermitian conjugate of any such expression. Some examples are as follows. Kets, inner products, matrix elements, outer products, composite bras and kets. Two Hilbert spaces V and W may form a third space VW by a tensor product. In quantum mechanics, this is used for describing composite systems. If a system is composed of two subsystems described in V and W respectively, then the Hilbert space of the entire system is the tensor product of the two spaces. If psi is a ket in V and phi is a ket in W, the direct products of the two kets is a ket in VW. This is written in various notations. See quantum entanglement and the EPR paradox for applications of this product. The unit operator. Consider a complete orthonormal system for a Hilbert space H with respect to the norm from an inner product. From basic functional analysis we know that any ket, psi, can also be written as with the inner product on the Hilbert space. From the commutativity of kets with scalars now follows that must be the identity operator, which sends each vector to itself. This can be inserted in any expression without affecting its value, for example, where, in the last identity, the Einstein summation convention has been used. In quantum mechanics, it often occurs that little or no information about the inner product of two arbitrary kets is present, while it is still possible to say something about the expansion coefficients and of those vectors with respect to a specific basis. In this case, it is particularly useful to insert the unit operator into the bracket one time or more. For more information, see resolution of the identity. 1 equals dx, xx equals dp, pp, where p equals dxexp, h, x, square root 2 pi h. Since x equals delta, plane waves follow x, p equals exp, square root 2 pi h.